Thank you for the introduction and thank you for inviting me here to it's a chance to give a talk here in ICECA. Uh, so the title of my talk is Exploring in Science Fiction. So I'll talk about science fiction conjecture and McDonald intersection polynomial, shuffle theorem, and other related stuff. And all these are based on joint work with Donghyun Kim and Seungjin Lee at Seoul National University and another based on another ongoing cowork with Donghyun Kim. Okay, here's the outline of my talk, and let me start with an introduction to Catalan numbers and QT Catalan number. And then in the second section, I'll explain the appearance of QT Catalan number in McDonald polynomials and this mysterious symmetric function nabla En. Then I finally introduce the science fiction conjecture and its relation to the shuffle theorem or nabla En. Finally, in the last section, I'll explain what I am doing these days to extend the science fiction conjecture and relate them to the Law-Warrington conjecture. So let me begin with the introduction to Catalan number. I think everyone here would know what Catalan number is. So Catalan number is our favorite sequence of integers. So I don't have to explain it, but I'll just say uh, the Catalan number defined by this nice product formula. So it's 1 over n plus 1 times 2n choose n. It starts with 1, 2, 5, 14, 42, and so on. And we love Catalan number because of its ubiquitous presence. So there's a saying among us that the Catalan numbers are everywhere. Indeed, Catalan number counts the number of dict paths, number of non-crossing perfect matchings, and number of triangulations of regular columns. So I'm not going to explain all these objects, but yeah, picture says more. And I'll just say that the dict path is a lattice path using up steps and right steps that never go below the main diagonal. And there are 5 dict paths of size 3, and the number 5 correspond to the third Catalan number. And all these 3 objects are counted by the Catalan number. And it is quite short list to say that Catalan numbers are everywhere. And in fact, Richard Stanley has cataloged more than 200 combinatorial interpretations of Catalan number, and you can check it in his book named Catalan numbers. And one might be curious if these appearance of Catalan numbers are within the realm of combinatorics, and it is not. It actually appears everywhere in every area of mathematics. And throughout this talk, I'm going to explain a few examples of Catalan numbers appearing in various fields of mathematics. And I'll give you 2 simple examples. And the first one is in geometry, so especially in Schubert calculus. I'm not going to talk about deep theory of Schubert calculus. I'll just introduce one of the original question of Schubert himself. So he asked, how many lines in n plus 1 space meeting 2n lines in general position? And the answer to this question is surprisingly given by the Catalan number. So this is the picture I downloaded from Frank Sotile's homepage. And so it's a R3, so it's a 3 space, and there are 4 lines, 4 blue lines in general position, and you can find 2 green lines, M1 and M2, meeting all those 4 lines. So this number 2 correspond to the second Catalan number. And there is another appearance of Catalan number in probability theory, especially in random matrix theory. So let Hn be the n by n Gaussian unitary ensemble. If you don't know, you can just think of it as a certain random matrix. So it's a unitary random matrix whose entries are given by certain Gaussian random variables. So it's a random matrix, and you may want to compute so-called the spectral moment to study the distribution of eigenvalues of your random matrices. And spectral moment is defined by this. So it's a expectation of trace of certain power of your matrix. And surprisingly, this normalized spectral moment converges to the Catalan number. And this appearance of Catalan number is not just a mere coincidence or just a fun fact. It actually very useful fact because it can be used to prove Wigner's semicircular, which asserts that if you take a Gaussian unitary ensemble and if you take an eigenvalues and draw a histogram or draw a distribution, then as n grows, it gets more and more similar to the semicircle. And this interesting fact can be proved using this identity involving Catalan numbers. So these appearance of Catalan number both in geometry or probability theory is not just a fun fact, it indicates that there might be a combinatorial structure hidden behind it. And as a combinatorialist, we can study those hidden combinatorial structure and contribute to the original fields. And for today's talk, we will see another appearance of Catalan numbers, but a more sophisticated version called the QT Catalan numbers. So as I already mentioned, the Catalan number counts the number of dict paths. So to be more precise, the dict path of size n is a lattice path like these, starting from 0, 0 all the way up to n, n using up steps or the right steps. And your dict path has to remain above the main diagonal. So there are 5 dict paths as we have seen. And to define QT Catalan number, I have to define 2 more statistics, DINV and area. And the first statistic, DINV, is a little complicated, so I'll try. So starting from the main diagonal, we travel to the left. And each time we meet the up steps, we label them starting from 1, 2, and so on. So for the first dict path, we label the first dict path, first up step by 1, and then meet the second up step, so label this by 2, and meet the third up step and label this by 3. Okay. And then you travel the second diagonal and do the same thing. So I'll give you another example here. So travel to the first, main diagonal, and you meet the up step, so you label this by 1. And you travel to travel the second diagonal, and you meet the up step, you label this by 2, and then travel again, you meet this, so you label this by 3. So in this way, you can label the up steps of your dict path from 1 to n. And then you read off these labeling starting from the first column bottom to top and the second column bottom to top and so on. Then we can associate a permutation to each dict path. So the first dict path, we have 3, 2, 1. So second dict path, we have 2, 3, and then 1. And the third dict path, we have 1, 3, and then 2. Okay. And now we can define the DINV, which is a diagonal invergence statistic. And you have already seen why diagonal comes up. And DINV is just an invergence statistic to the permutation associated to the dict path. So DINV of this first dict path is an inversion number of this permutation, so it's 3. So there are 3 numbers that are out of order, 3 pairs of numbers. And DINV of this dict path is given by inversion number of this guy, so it's 2. Okay, so we have defined the first statistic DINV, and the second statistic area is much simpler to define. It is just the number of boxes between the blue dict path and the black main diagonal. So since there are no boxes here between the blue one and the black one, so the area is 0. And for the second dict path, we have full box here. There is only 1 box, so the area is given by 1. Okay, and we can compute all these using our hand. And the QT Catalan number is defined as a generating function over dict path using these 2 statistics, DINV and area. So according to the computation, the third QT Catalan number is QQ q squared t, qt squared plus qt plus tq. Okay, so, and this expression here for the third qt Catalan number will appear repeatedly throughout my talk, so I ask you to remember this. And to emphasize it, I will just repeat. The third qt Catalan number is qq plus q squared t plus qt squared plus qt plus tq. And as you can see, this qt Catalan number is kind of a sophisticated version of Catalan number. So you may be worried that the ubiquitous presence of Catalan number may have disappeared. But the interesting thing is that it is still everywhere. So the qt Catalan number appears in various settings in maybe geometry, topology, or representation theory, or still in combinatorics. So they appear in McDonald polynomials, diagonal covariance, Strohanovic Keke algebra, knot invariance, positroid Hilbert scheme, and elliptical algebra, and so on and so on. Uh, I'm not, I don't have time, or I don't have enough knowledge to. Oh, there's a question about, yeah. So I just so the, I'm I'm a bit familiar with another way of defining this dim statistic, and I just learned that this there is another way, like I just explained. There is another way to associate a permutation to each dict path like this, and then counting inversion number for that. And Michael just asked that if the permutation that comes up like this way is there's some pattern avoidance properties, and that thing I don't know. I mean, yeah, I haven't checked, and maybe yes, maybe. Anyway, I don't. Yeah, thank you for the question. And uh, for these various topics, I don't have time and I don't have enough knowledge to explain it all. So for today's talk, let me focus only on the first two, McDonald polynomials and diagonal covariance. Yeah. Is there another question so far? Okay, if not, let's proceed to define the McDonald polynomials. Before that, I have to set up some notation and review some backgrounds. So as usual, I'll denote the monomial symmetric function by m lambda, the elementary symmetric function by e lambda, and the short functions by s lambda. And all these symmetric functions are basis of the ring or space of the symmetric functions, and this lambda is an integer partitions. And studying symmetric function is important in a sense. And one of the reasons is that studying symmetric function is more or less studying the symmetric group Sn representation theory. Indeed, there is a isomorphism called the Frobenius characteristic map, which sends the irreducible module called the spect module as super lambda indexed by partitions to the short function S lambda. In this way, short function is of particular interest and importance. And it is indeed in combinatorics, it is often very important to find or prove certain function, certain symmetric function is sure positive. And by sure positivity, I mean, if your symmetric function f expanded into short function, if all the coefficients c lambda are lying in non-negative integers, or more generally, if they are polynomials in Q and T with non-negative integer coefficients, we say that the symmetric function f is sure positive. And this sure positivity may indicate that there might be a representation theory, or there's an SN module that explains the sure positivity or sure coefficient as a decomposition number of that module into irreducible. So finding sure positive functions or proving it is very important question in algebraic combinatorics. And in today's talk, we will see lots of examples of sure positive symmetric functions. And one example is the McDonald polynomials. So McDonald, in his seminar paper in 1988, defined his named polynomial the Macdonald polynomial, is a symmetric function in x variables, x1, x2, and so on, with two additional parameters, q and t. And his original motivation was coming from Selbach integral and Dyson's conjecture. And if I have to say the importance of Macdonald polynomial just in one sentence, I would say Macdonald polynomial is important because it is a universal symmetric function. And by universality, if you specialize the parameters q and t into certain values, then it recovers every symmetric function that I have mentioned today. So monomial symmetric function m lambda, short function s lambda, and the elementary symmetric function e lambda. Moreover, it recovers another important families like whole-literal symmetric functions, Whittaker symmetric functions, or Jack symmetric functions. So somehow studying Macdonald polynomial is not just studying a single family of symmetric function, it is a studying of all these various kinds of symmetric functions all at once. Okay. And this is actually, to be honest, this is not H tilde, but this is a Macdonald P polynomial, but for today, I'll just abuse our notation, or I'll just say all those are Macdonald polynomials. They're just variants. Okay. And one of the important question or conjecture of Macdonald himself was Macdonald positivity conjecture. So these are Schur expansion of Macdonald polynomials. And you can directly see that the Schur coefficients are just the polynomial in Q and T with only non-negative integer coefficients. And it is a very surprising fact that there is a Schur positivity if you see the definition. And this fact, this Schur positivity was proven by Mark Heyman in 2001 using geometry of Hilbert scheme. And actually, Garcia and Heyman constructed their named module R mu, so Garcia-Heyman module R mu, indexed by partition. And what Heyman proved is that the Garcia-Heyman module is the representation theoretic model. So SN representation theoretic model for the Macdonald polynomial. So the Schur coefficients of Macdonald polynomial is just the decomposition number of this Garcia-Heyman module, so thereby proving the Schur positivity. And even though Heyman proved the Schur positivity, it is still unknown how to give an explicit combinatorial interpretation for this Schur coefficient, and called the Macdonald-Koska polynomial or QT-Koska polynomial. And this is one of the major open problem in algebraic combinatorics, and this guided lots of breakthrough and my research too. And along the way, people studying this Macdonald positivity or trying to attack this major open problem, people noticed that it is very useful to use certain operators that act on symmetric function array. And the Nabla operator is one of such example. So the Nabla operator defined by Bergeron-Garcia or Bergeron-Garcia-Heyman-Tesler is an eigenoperator to the Macdonald polynomial. And the eigenvalue T mu is the last Schur coefficient of Macdonald polynomial. So for example, T3 is Q cubed, T21 is QT, and T111 is TQ. Okay. Since Macdonald polynomials are basis of symmetric function, so Nabla not only defined on the Macdonald polynomial, it is defined on the symmetric function. So you may want to apply this Nabla operator to other symmetric function, maybe like the symmetric function En, the elementary symmetric function. And surprisingly, you can directly observe that this Schur expansion only involves the plus sign, so there is no negative signs at all. So you can directly observe that Nabla En is also Schur positive. And to make the second observation, I highlighted the last Shor coefficient into red. And if you plug in Q and T equals to 1, then this guy is 1, this guy is 2, and this guy is 5, which are the first, second, and the third Catalan number. So you can find some Catalan numbers here. And actually, if you look closely, this guy here, Q cubed plus Q squared T plus QT squared plus QT plus T cubed, is the thing that I ask you to remember. It is the third QT Catalan. So we can observe that the last Shor coefficient of this nabla En is given by the nth QT Catalan. And these observations leads various breakthrough in this area. And I'm going to introduce three of them. So the first one is a verification of the first observation, the Shor positivity. So there is a SN module called the diagonal covariant, which is a quotient of this polynomial ring in two n variables by this invariant idea where the SN action, symmetric group action, is given by permuting these two n variables diagonally. And Mark Heyman again proved that the bigraded Frobenius characteristic of this diagonal covariant coincide with this symmetric function nabla En, thereby proving the Shor positivity of this nabla En. And this theorem is also called the n plus 1 to the n minus 1 conjecture because he also proved that dimension of DRN is n plus 1 to the n minus 1, which is the number of parking functions, spanning trees, and so on. Anyway, the second observation is proved by Garcia and Hegland in 2001, and they proved the second observation. So the last Shor coefficient is given by the QT Catalan number. And the third breakthrough I'm gonna explain is the shuffle theorem, eventually proved by Carson and Mallet and conjectured by Hegland, Heyman, Lohr, Remmel, Ulyanov in 2005. It is about not Shor expansion, but monomial expansion, but full monomial expansion, explicit combinatorial formula for nabla En. And this might look complicated, but it involves the path and slightly generate a generalized notion of parking function and two statistic Dean-Van area, which is very similar to Dean-Van's area for the dict. And I would like to refer the right-hand side to the as a shuffle formula and denote this by Dn. And these are actually a very, very good result and indeed a breakthrough. So I'm enjoying this day reading interviews in ECA journal, and I looked up like every interviews and ask almost every time like what three results are most influential in combinatorics in 30 years. And Richard Stanley, the first speaker at the first talk in this conference, and Schilling, Vic Reiner, who was the first speaker of the yesterday's conference, and Xavier Viennot, they all chosen the n plus 1 to the n minus 1 theorem of Heyman or shuffle theorem of Carson and Mallet or Garcia and Hegland's result about QT Catalan number. So these results are indeed a breakthrough, and it is influential to many researchers after all these 30 years. And so we have seen two appearances of Catalan number in McDonald polynomial theory or diagonal covariance. And today's talk, so all the thing that I have explained is kind of a history. And in today's talk, I'm going to explain my new results about a new appearance of QT Catalan number in the science fiction conjecture. Okay, so let's begin the third section. So I prepared for another interview. It's the same interview of Richard Stanley. And Richard Stanley also got asked a question like, what are the top three open questions in your list? And the first question was Schubert's structure constant. And the second problem was Stanley-Stanbridge conjecture about E positivity of chromatic symmetric function. And the third question was like, if Young's lattice is the smallest differential poset. And this is the Young's lattice, so lattice of partitions, as you all might know. And but he added one more conjecture in his list, and he said a more serious problem would be proving a plethora of conjectures called a science fiction by Adriano Garcia and François Bourgeois. So, what is the science fiction and why is it important? Before I talk about science fiction conjecture, let me give you a motivating example and explain what Butler's conjecture is. So here are here is short expansion of McDonald polynomials. And as we have seen, McDonald polynomials are Shor positive. But for now, we want to refine this observation, refine this Shor positivity. To make the observation easier, I highlighted some of the coefficients into blue and the other coefficients into red. And you might directly see that the blue parts are the same. So the blue parts can be thought of as an intersection of these two McDonald polynomials because they both lies in H3 and H2. So they can be considered as an intersection. The red parts, on the other hand, they are different, but they're not just different, their ratios are the same. So Q square over T, so Q square over T is equal to Q cubed over QT. And the last short coefficient was T mu, so we can write it as T3 over T21. And if you want to extract only the blue part, only the intersecting part, you can do this following divided difference. So you can multiply the right ratio to your McDonald polynomials and take a difference to eliminate the red parts and divide all those by the difference of the ratio to recover the blue parts, S3 plus Q times S2. And I denote this new symmetric function by I3,21 because it is an intersection of H3 and H2. And by construction, it is Shor positive because we try to extract only the blue parts. But what Butler conjecture is more general thing. So starting from two partition, where the second partition is obtained from the first one by moving a cell. So mu and lambda is very similar partition, very similar to partition, and you compute the similar divided difference like this, and define this as I lambda mu. And what Butler conjectured in her 1994 paper is that her symmetric function I lambda mu is always Shor positive. I would like to introduce my results involving related to Butler's conjecture. And let me recall that one more celebrated result of HHL. So Hagelin-Heyman-Lohr formula is not a Shor expansion, but explicit monomial expansion of McDonald polynomials. So it's a breakthrough step towards the Shor expansion of McDonald polynomials. And it involves two intricate statistics, in mu and match mu, and it is a generating function over wars or permutations. So even though we failed to prove the Shor positivity of I lambda mu, we gave an explicit combinatorial formula for the monomial expansion. So monomial positivity, more than monomial positivity, we have found the explicit formula. So we somehow pinpointed which words in this W nu are in the blue part and which words are in the red part. So which words are different ratio and which words are the same thing. By doing that, we could refine this HHL formula to give a precise formula for this symmetric function I lambda mu. And we actually proved the Butler's conjecture for some particular cases. Okay, and this is what we have done for Butler's conjecture. Since Butler's conjecture is about sure positivity, one may ask, so every symmetric function we have seen today, McDonald polynomials and nabla En, which are sure positive, the sure positivity is proven not in the means of combinatorics, but in the means of geometry or representation theory. So one may ask if there is a representation theoretical model for Butler's symmetric function, I lambda mu. And let's recall that Heyman proved in the n factorial theorem, first that the McDonald polynomial is a Frobenius characteristic of Garcia-Heyman module. And what Bergeron and Garcia noticed is that this Butler symmetric function I lambda mu is actually the Frobenius characteristic of intersection of two Garcia-Heyman modules, R lambda and R mu. Thereby, sure positivity follows. So they have not proved it, but they have a computation and conjecture this connection. So I just said the blue parts are the intersection, but it was not just a metaphor. It is indeed intersection of McDonald polynomials, or more precisely, the Frobenius characteristic of intersection of Garcia-Heyman module. So this intersecting part actually refines the McDonald polynomials. So by studying this refinement, we could study the whole structure of McDonald polynomials. So this is very nice observation, but Bergeron and Garcia didn't stop there. So they pushed up their ideas to finally construct a science fiction conjecture. And to explain what is the science fiction conjecture, let me start with a partition mu. And starting from this partition mu, we remove corners one by one. So if we remove the first corner, we obtain the new partition mu1. And if we remove the second corner, we name it mu2. And third, if we remove the third corner to obtain mu3, we remove the fourth corner to obtain mu4. So we obtain new partitions, mu1, mu2, mu3, mu4 by deleting a corner one by one. Okay. And then by mimicking the way Butler defined her symmetric function I lambda mu, we could define this McDonald intersection polynomial as a linear combination of McDonald polynomials and denoted by I mu1 through mu n. And what Bergeron and Garcia, the science fiction conjecture, implies is that this McDonald intersection polynomial is indeed the intersection of McDonald polynomials. So it's a Frobenius characteristic of intersection of all those Garcia-Heyman modules, R mu1 through R mu n. Okay, and they have also conjectured as an n factorial theorem counterpart, the dimension of this intersection is always given by n factorial as usual, but divided by the number of corners. So it is also called the n factorial over k conjecture. So we use the different notion for n, but yeah, let's just forgive me for that. So these two are consequences of science fiction conjecture. And to be honest, science fiction conjecture is very widely open, and I think we don't know much about Garcia-Heyman modules or their combinatorics. But still, we can study this right-hand side, the symmetric function called the McDonald intersection polynomial by means of algebraic manipulation or using combinatorics. And that is what we have done. Okay, so we started some observation of this McDonald intersection polynomial. And the first observation we made is this one. So this example is McDonald intersection polynomial of these four partitions, mu1, mu2, mu3, and mu4. And to make the observation easier, I omitted all the other things and highlighted only the last Shor coefficient. And by scaling out, the last Schur coefficient is given by q cubed plus q squared t plus qt squared plus qt plus t cubed. And once again, we meet the third qt Catalan number. So what we have observed and proved is that for Macdonald intersection polynomial, the last Schur coefficient is always given by n minus 1 to qt Catalan. And recall that the shuffle theorem generalizes this qt Catalan combinatorics to the combinatorics of parking function and the full monomial extension. And we also prove that our symmetric function, the Macdonald intersection polynomial, is related to both nabla en-1 and the shuffle formula dn-1. So I just wanted to highlight that the proof of part A and proof of part B is independent. So we proved part A by using Garcia-Heyman-Tesler's platistic formula for Macdonald polynomials, so by means of algebra. And we proved part B by using combinatorics. So we used HHL formula and column exchange rule that we have developed and so on. So by proving this part A and part B independently, we could prove that right-hand side of A and B are the same, which is the shuffle theorem. So we, as a corollary, we could provide a new proof of shuffle theorem. So somehow, I think studying Macdonald polynomial is important, and I think we have found another reason why this is important, because in this red parts here, this is an intersection of all these three Macdonald polynomials given by the Macdonald intersection polynomial. And we have found that by squeezing it, by skewing, we could find this nabla en-1, which is the main object of the shuffle theorem. So to understand this Macdonald intersection polynomial, we may need more sophisticated, more complicated combinatorics, more beautiful combinatorics that we have developed for the shuffle theorem. So there's lots of things we have to do. Okay, and for the remaining 10 or so minutes, I'm gonna talk about what we are doing right now. So we are trying to extend or generalize the science fiction conjecture and relate them to the Lower-Warrington conjecture. So let's recall that science fiction conjecture is about intersecting Garcia-Heyman modules or Macdonald polynomials, so to speak. So the blue part is just the Macdonald polynomial, and the green parts are intersection of mu1 and mu2. And the red part is intersection of mu1, mu2, and mu3. And all of them are Schur positive. And moreover, the difference of them are Schur positive too. So somehow these Macdonald intersection polynomials give a filtering of Macdonald polynomial. And we will see that these blue parts, green parts, and red parts can be considered as this new symmetric function, h tilde mu1 super lambda, where lambda is a one row partition. So empty partition, one cell, or one row partition of two cells. Okay. So I'm going to define what these are. And to define this new symmetric function, I need an intermediate symmetric function, I mu lambda k. So let's say mu is a partition of n removable corners, and let's fix k between 1 and n. And we also choose a partition lambda, which sits inside this rectangular partition n minus k to the k. Then so recall that mu I was mu minus the ith corner ci. So generalizing it. So for each subset S, so for each k subset of n, we define a new partition mu S, by removing corners Ci indexed by S from the partition mu. So we are removing K corners at once. Then we define a new symmetric function, generalizing the way we define the Macdonald intersection polynomial. So it's a linear combination of Macdonald polynomials indexed by mu S, but there are certain rational functions in Q and T before that. Okay, and we conjecture that this new symmetric function is actually a generalization of Macdonald intersection polynomial. It is conjectured to be sure positive with global signs. And indeed, if we choose our K to be 1 and lambda to be empty partition, it is indeed a Macdonald intersection polynomial. So it is a generalization of Macdonald intersection polynomial. And using this intermediate symmetric function I mu lambda K, we can define the symmetric function that I promised to define, like H tilde lambda, H tilde mu K, super lambda. And I'm not going to define it precisely, but I'll just say that this is certain divided difference operator that act on the symmetric function. And yeah, there is certain way to define this notion. And if we take our lambda to be one row, it recovers the Macdonald intersection polynomial. And in our ongoing cowork with Dong-Young Kim, we conjectured, so this is a generalization of science fiction conjecture. So we conjectured that this new symmetric function, H tilde mu S super lambda, is a Frobenius characteristic of intersection of certain Garcia-Hamilton modules. So what is this lambda acted on S? So I'll explain this by examples, okay? So let's start with a partition lambda, and let's index each column by 1, 2, 3, and so on all the way up to K. And then we index the rows starting from K plus 1 and K plus 2 all the way up to N. Then think of all these three cells as a coordinate. So it's 1, 3, it's 2, 3, and it's 1, 4. Okay. And then we start with a subset 1, 2. So this is 1, 2. So we start from 1, 2. Okay. And if we choose empty partition, then it is just 1, 2. And it is a full Macdonald polynomial here in the Venn diagram. And if we choose our lambda to be one cell, then we have to act this cell to the subset 1, 2. And this cell acts by transposition of 1 and 3. So we have 1, 2. So we leave our 1, 2 here. And if we apply the transposition 1, 3, and then we will get 2, 3, right? So we add 2, 3 into our list. And this new symmetric function will correspond to the intersection of Garcia-Hamilton module indexed by 1, 2, and 2, 3. So it's an intersection of R mu 1, 2 and R mu 2, 3. So in this picture, it is right here. And if we want to apply this one row, then we have to additionally apply this second cell here, which is 2, 3. So we apply the transposition 2, 3. And if you apply 2, 3 to this subset 2, 3, then nothing happens. So we do not add anything. But if we apply transposition 2, 3 to the subset 1, 2, then 2 becomes 3, so it's 1, 3. So we add 1, 3 to our list. So finally, we can say that like these one row apply to 1, 2 is these three lists, 1, 2, 2, 3, and 1, 3. And we conjecture that this new symmetric function indexed by a one row partition is given by the Frobenius characteristic of intersection of three Garcia-Hamilton modules R mu 1, 2, R mu 2, 3, and R mu 1, 3. So it's pictorially it corresponds to this part. And finally, if we apply the full lambda, and we have to apply one more transposition 1, 4, and we add 2, 4, and 3, 4 to our list, then we what H tilde super lambda means is that intersection of all these 5 Garcia-Hamilton modules. So in this picture, we have this part here. So somehow we generalized the science fiction conjecture to these kinds of complicated way to get these partitions and intersecting all those Garcia-Hamilton modules. And we also have a conjecture as a counterpart of n factorial over k conjecture. So as I already mentioned, one row partition is corresponding to the McDonald intersection polynomial, or intersecting Garcia-Hamilton modules, or R mu I. And science fiction conjecture suggests that the dimension of it is n factorial over k. And more, so somehow we associated the number 1 over k to the partition, one row partition k minus 1. In general, since we have defined H tilde super lambda, we can associate for each partition lambda to ratio of dimension of Garcia-Hamilton module and intersection of Garcia-Hamilton module associated to that lambda. And these are the numbers that we have newly defined. So all these one row partition, the numbers are k plus 1, 1 over k, and all these blue numbers are mu. And I believe these numbers are of independent interest because we have observed that these numbers satisfy some Beery type rule, and there's some patterns about sum over hooks or staircase shape or one column shapes. So I think these numbers are very interesting and worth of study. And for now, we have extended science fiction conjecture and newly defined new symmetric functions like I mu lambda k and H tilde super lambda, and how it is related to the Low-Warrington conjecture. And let's recall that the shuffle theorem of Carson-Mellett is about the monomial expansion of nabla En, and it involved the combinatorics of Perkin function, or the Catalan numbers, or dick path. And there's a generalized notion of nested dick path, which looks like this. Oh. And this symmetric function En is just the Shor function indexed by one column partition. So one may ask, what happens if we replace En to the general Shor function? And Lohr and Warrington conjectured that the monomial expansion of this nabla Shor is governed by the nested dick path that I have showed you. And this Lohr and Warrington's conjecture in 2008 is very recently proved by Blasha, Kamen, Morse, Poon, and Sillinger in 2021. And in the ongoing work with Dong and Kim, we have found that the last Shor coefficient, which is a Qt count of nested dick path, so I'll just call it Qt nested Catalan number, also appears as in our new symmetric function I mu lambda k. And we have also proved that so part A, so if you skew the symmetric function I mu lambda k with elementary symmetric function, it gives you the nabla Shor function. And independently, we could prove that I mu lambda k skewed by elementary symmetric function, it gives a Low-Warrington formula, the combinatorial formula. So since we have proved part A and part B independently, we could also prove the Low-Warrington conjecture. So we could provide a new proof of Low-Warrington conjecture by using part A and part B. And I think our method is very elementary and very combinatorial. It uses combinatorics of p-tableau that appears in chromatic symmetric function, and we use this Scherchen-Wax involution in chromatic symmetric function theory and so on. So it's very combinatorial, and I think it's readable to everyone. Yeah, and it's coming up maybe in September on our. And thank you for your attention, and this is all I have for today.